Green chemistry aims to reduce chemical-related impact on human health and virtually eliminate contamination of the environment through dedicated, sustainable prevention programs. Green chemistry searches for alternative, environmentally friendly reaction media and, at the same time, strives to increase reaction rates and lower reaction temperatures. The green chemistry concept applies innovative scientific solutions to solve environmental issues posed in the laboratory. Paul T. Anastas, an organic chemist working in the Office of Pollution Prevention and Toxins at the EPA, and John C. Warner developed the 12 Principles of Green Chemistry in 1991. These principles can be grouped into reducing risk and minimizing the environmental footprint. Framework of Green Chemistry. The three main points about the green chemistry framework can be summarized as 1. Green chemistry designs across all stages of the chemical life cycle. 2. Green chemistry seeks to design the inherent nature of the chemical products and processes to reduce their intrinsic hazard. 3. Green chemistry works as a cohesive system of principles or design criteria. The 12 Principles of Green Chemistry are design criteria or guidelines that provide the framework for sustainable design. They constitute an overarching construct for the design of safer chemicals and chemical transformations. Chemistry has long been perceived as a dangerous science, and often the public associates the word chemical with toxic. There are ways to reduce risk by using safety precautions such as protective gear. When safety protections fail, the risk, which is defined as a function of the hazard and exposure, increases. If the hazard is high and exposure controls fail, the consequences can be catastrophic, injury, or death. By minimizing the hazard portion of the equation, instead of focusing only on exposure controls, the risk can be limited even in cases of undesirable circumstances, accident, spills, sabotage, etc. Designing safer, sustainable chemicals and processes requires striving to reduce the intrinsic hazards to a minimum, and, therefore, limiting the risk of accidents and damage. The aim of green chemistry, to reduce hazards across all the life cycle stages, is economically profitable. Hazard is defined as the ability to cause adverse consequences to humans or the environment. Intrinsic hazard of a chemical substance or a chemical process can be designed to be minimized at every level of a process, whether it is toxicity, physical hazards, e.g., explosion, flammability, or global hazards, such as stratospheric ozone depletion. Risks based on these hazards may arise from the nature of the feedstock and raw materials that are used in the chemical transformations, as well as the final products that are made. Careful design will reduce or eliminate intrinsic hazards within chemicals and processes. A design based on the integration of the 12 principles as one cohesive set. The 12 Principles of Green Chemistry were introduced in 1998 by Paul Anastas and John Warner. They are a guiding framework for the design of new chemical products and processes, applying to all aspects of the process life cycle from the raw materials used to the efficiency and safety of the transformation, the toxicity and biodegradability of products and reagents used. They were summarized recently into the more convenient and memorable acronym PRODUCTIVELY. The acronym PRODUCTIVELY summarizes the 12 Principles of Green Chemistry, helping chemists remember key sustainability goals like preventing waste, using renewable materials, designing degradable products, using catalysts, ensuring temperature-pressure ambient, monitoring in-process, minimizing auxiliary substances, very few, maximizing feed, E-factor, ensuring low toxicity, and being inherently, safe, along with omitting derivatization steps and focusing on atom economy, implicitly included. 1. Waste. Waste prevention is the first of the 12 Principles of Green Chemistry. It is better to prevent the formation of waste rather than to clean it up after the fact. The generation of any material that does not have realized value or the loss of unutilized energy can be considered a waste. As mentioned above, waste can take many forms and may impact the environment differently depending on its nature, its toxicity, its quantity, or the way it is released. When large portions of the initial raw materials used in a process are lost because of the original design of the process itself, then it will inexorably generate waste, which is by definition undesirable. In 1992, the concept of what is now widely accepted as the E factor, or environmental impact factor, was introduced by Roger Sheldon. This metric helps to quantify the amount of waste generated per kilogram of product. It is a means to assess the environmental acceptability of a manufacturing process. The environmental factor, which has been adopted by many in the chemical industry, underscores how inefficient certain industrial processes have been and opened the door to creative solutions. One well-known example is the early synthesis of ethylene oxide, which was prepared through a chlorohydrin intermediate. The E factor for the entire synthesis was equal to 5. For each kilogram of product, 5 kilograms of waste were to be disposed of. This does not take into consideration the wastewater contaminated by chlorine byproducts. When the synthesis was modified to use molecular oxygen, thus removing the need for chlorine, the E factor dropped to 0.3 kilograms of waste. The new process was generating more than 16 times less waste than the original one, eliminating the formation of wastewater as well. 2. Atom economy. In 1990, Barry Trost introduced the concept of synthetic efficiency. Atom economy, AE, also called atom efficiency. It refers to the concept of maximizing the use of raw materials so that the final product contains the maximum number of atoms from the reactants. The ideal reaction would incorporate all of the atoms of the reactants. The AE is measured as the ratio of the molecular weight of the desired product over the molecular weights of all reactants used in the reaction. It is a theoretical value meant to quickly assess how efficient a reaction will be. 3. Synthesis. The synthetic toolbox of organic chemists has been improved by a significant amount of innovative work. Many of the new reactions that have been developed in the past decade add to the already existing green reactions that were discovered during the past century. Reactions based on cycloaddition, rearrangement, or multi-component coupling reactions were already known and constitute one category of efficient reactions. Cascade or tandem reactions, CH activation, metathesis, and enzymatic reactions are rather new approaches and illustrate strong examples of cleaner, more efficient synthetic tools available to organic chemists. The Grubbs catalyst, for example, allows alkene metathesis through a mechanism similar to Wittig-type reactions, such as the Horner-Wadsworth-Emmons reaction, formation of a four-membered ring as reaction intermediate. It is an essential tool for the construction of larger molecules. However, unlike the Wittig reaction, the metathesis reaction does not produce a large amount of waste. 4. Molecular design. While there has been significant focus on designing chemicals for various functions ranging from medicines to materials, there has been a surprising lack of interest in taking into consideration hazards in the design process. Understanding the properties of a molecule that have an impact on the environment and the transformations that take place in the biosphere is essential to sustainability. Through a mastery of this understanding, chemists will be able to genuinely design molecules that are safer for humans and the environment. Work by Arians in 1984 and by Garrett and DeVito in 1996 showed that designing safer chemicals is not only highly needed for the advancement of green chemistry, but is also possible. 5. Solvents. Solvents are perhaps the most active area of green chemistry research. They represent an important challenge for green chemistry because they often account for the vast majority of mass wasted in syntheses and processes. Moreover, many conventional solvents are toxic, flammable, and/or corrosive. Their volatility and solubility have contributed to air, water, and land pollution, have increased the risk of workers' exposure, and have led to serious accidents. Recovery and reuse, when possible, are often associated with energy-intensive distillation and sometimes cross-contamination. In an effort to address all those shortcomings, chemists started a search for safer solutions. Solventless systems, water, supercritical fluids, SCF, and, more recently, ionic liquids are some examples of those new green answers. 6. Energy. Rising concerns over the depletion of petroleum feedstocks and the increase in energy consumption have pushed the development of more energy-efficient processes and the search for renewable energies, non-depleting resources, in a time frame relevant to human scale. As mentioned in the first principle, unutilized energy may also be considered a waste. The design of chemical reactions or systems that do not require intensive energy use is highly desirable. Reducing the energy barrier of a chemical reaction or choosing appropriate reactants so that the transformation may proceed at room temperature is one example of what chemists can do to reduce energetic requirements, with all the direct and indirect benefits associated with it. 7. Renewable materials. It has been estimated that the vast majority of our manufacturing products are derived from petroleum feedstock or natural gas. The depletion of those resources will touch many aspects of our consumer life and our economy. Turning towards renewable feedstocks, both for material and fuel, has now become more urgent. The major renewable feedstock on the planet, both for material and energy, is biomass, the material available from living organisms. This includes wood, crops, agricultural residues, food, etc. Examples of renewable material include cellulose, lignin, suberin, and other wood compounds, polyhydroxyalkanoates, lactic acid, chitin, starch, glycerol, and oil. Lignin, for instance, is a major waste of the pulp and paper industry. 8. Derivatives. Covalent derivatization is a ubiquitous technique in chemistry, whether it is employed for organic synthesis or analytical chemistry. In the early 1990s, an innovative concept surfaced called non-covalent derivatization, a derivatization that does not rely on covalent bonding, but rather on intermolecular interactions. The work by Warner was developed as a means to use little energy and less material to achieve chemical modifications from the original system. An early example of non-covalent derivatization is illustrated by the controlled diffusion and solubility of hydroquinones used in Polaroid films. Researchers at Polaroid sought to release hydroquinones at elevated pH. Instead of relying on base-label covalent protecting groups, which would be the traditional approach, they developed a non-covalent protecting group in the form of a co-crystal between hydroquinones and BIs, N-dialkyl terephthalamides. This approach was successful and viable for the industrial process. It solved the problem without modification of the original hydroquinone structures and minimized waste material and energy. 9. Catalysis. In many cases, the formation of waste is linked to the traditional use of a stoichiometric amount of reagents. Switching from stoichiometric methodologies to catalytic processes is perceived as one major way to improve the efficiency of the synthetic toolbox. Catalysis can improve the efficiency of a reaction by lowering the energy input required, by avoiding the use of stoichiometric amounts of reagents, and by greater product selectivity. This implies less energy, less feedstock, and less waste. 68. Moreover, it often opens the door to innovative chemical reactions and brings unconventional solutions to traditional chemical challenges. Oxidation and reduction reactions illustrate this concept. Reduction employing DIBALH as the hydride donor is a well-established procedure used by organic chemists. It generates a significant amount of waste since a stoichiometric amount of reducing agent is needed to complete the reaction. Switching to catalytic hydrogenation, like the Noyori hydrogenation, eliminates the need for stoichiometric reagents and, in consequence, decreases the amount of feedstock needed and the amount of waste generated. 10. Biodegradation. The problem of persistence has been known for a long time and became apparent in the early stages of industrial development. In the 1950s, for instance, tetrapropylene alkylbenzene sulfonate, TPPS, was used as a surfactant for laundry detergents and accumulated in the water supply due to incomplete degradation. The situation was so critical that there were examples where water tended to foam when coming out of the tap. The public outcry prompted the industry to seek an immediate solution, and it was found that replacing the methyl-branched chain of TPPS with a linear carbon chain reduces the biopersistence. A common example is the replacement of TPPS by linear alkylbenzene sulfonate LAS. 11. Analysis. It is the goal of green analytical chemistry to measure chemicals without generating waste. The environmental issues associated with analytical chemistry are usually linked to the analytical approach itself. Real-time direct analysis is unfortunately not systematic, as many methodologies still require a pre-treatment of the sample or rely on what one may call ex situ analysis. Process analytical chemistry is defined as the ability to monitor a transformation and act immediately upon it to prevent unwanted outcomes. It is not always possible, and therefore, waste may be generated when the sample is analyzed. Green chemists must take into consideration the functional requirements of analytical methods, since it will be counterproductive if the chosen methods contribute to further environmental problems. Green analytical chemistry can be defined as the use of analytical procedures that generate less waste and are safer to human health and the environment. This definition includes both aspects of live monitoring of a chemical transformation and the environmental shortcomings associated with traditional analysis. In situ, monitoring of a reaction has significant advantages in terms of green chemistry. When action can be taken quickly, it may prevent accidents, save energy, and/or prevent the formation of significant amounts of byproducts that would otherwise require additional purifications. 12. Accident prevention. Dangerous substances and processes have multiplied in our working environment. According to the Chemical Accident Prevention and the Clean Air Act amendments of 1990, preventing accidents starts by identifying and assessing the hazards. All types of hazards, whether it is toxicity, physical hazards such as explosivity or flammability, and global hazards, should be addressed in the design of chemicals and processes to prevent accidents such as Bhopal or the Love Canal incident. A recent and shocking illustration of these dangers and hazards can be found in the UCLA accident that occurred in January 2009. Handling of the very common and highly flammable butyllithium reagent resulted, unfortunately, in a terrible outcome with the death of the research assistant involved. This accident should be a strong reminder to the scientific community that many chemicals we still use present serious hazards and should be replaced by safer alternatives to prevent accidents wherever possible. The accomplishments in the field of green chemistry thus far are impressive due to the scientists in academia, industry, and research institutes around the world. However, the accomplishments achieved thus far are a prelude to the grand challenges still to be addressed by the field. A few notable challenges are mentioned below. The design framework of the 12 Principles of Green Chemistry has been a template for many advances in the field. However, the 12 principles were not meant to be 12 independent goals, but rather an integrated, cohesive system of design. Only by applying all principles can one hope to achieve a truly sustainable process. By seeking out the mutually reinforcing aspects of the principles, systemic sustainable design is possible and can facilitate transformative innovation rather than incremental improvement.